Today we're going to look at Physics Achievement Standard 2.6, answer question from 2012 on static electricity. This one talks about Millikan's experiment where he determined the charge of an electron. He placed an oil drop between two charged plates and calculated the strength of the electric field needed to stop the oil drop from falling. So looking through this question completely first, we're going to look at all the steps and then go back and solve it. Strategy that you would want to use in a test as well. So, question part A asks you why the battery is connected the way it's shown. And from this, you're going to have to look at the when you're looking at electricity, DC electricity. We're going to come back to this. So it's just asking why is the battery set up the way it is. Part B says that in terms of forces, state the conditions necessary for the oil drop to be held stationary between the two plates. So we're going to take a look at the oil drop and take a look at the forces that are being applied on it. Part C is where you got to do your calculations. It says that on one occasion, Millikan used an oil drop with a mass of 2.54 10 to the negative 5th kilograms with a charge of 3.6 10 to the negative 9th coulombs. Plates were 4.8 meters, or times 10 to the negative 4th meters apart. Calculate the voltage needed to hold the oil drop stationary between the two plates. So we've got oil drop there, and we need to calculate the voltage Millikan used in this particular experiment to hold this drop stationary. So what it's asking there is for the voltage. And then for part D, we want to express our answer from part C to the correct number of significant figures. This is nice to know that we've already read through all of this, so as we're going through each of the other parts, we can go ahead and express things in significant figures and just make it easier for us, and that way we don't have to go back and do that later. So I think that it's easier to skip part A and go straight to part B. That's going to make it a little bit easier to solve for what part A is asking. So part B, taking a look at the forces. We've got gravity pulling down, and then we have an electric field pulling back up. And because this is stationary, we can go ahead and label this force of gravity, and this one the force of the electric field. And because the oil drop is stationary, we know that both of these forces are going to be equal. The other thing that I already did, but that I would have done right at the beginning, is I've made a list of all of the variables that I either know or that I might want to know while solving this question. That I'll list out, and all the ones that I know I've already plugged in, including units over here. So we can start filling those in at some point. So for B, force of gravity, force of electric field, and they are equal. That's all you need for that one. Knowing that, we can go back to part A. It's asking why the battery is connected as shown. So we've got positive end here and the negative side here, which means our plate A is going to have positive charges on it, and plate B is going to have negative charges on it. Since we were told in part C that the charge is negative, then we know that the electric field is going to push the oil drop up, which makes sense because we know that it's stationary, gravity is pulling it down, electric field is pulling it up. If this was reversed, the oil would just drop even faster than gravity. There'd be two forces pulling it down in the same direction. So solving for part C, there's a couple of ways we can go about this. There's definitely going to be a sequence of events that we're going to have to solve. We've got a lot of blank information over here, and since we're trying to find voltage that's going to be our final answer, but we don't know both the distance and the strength of the electric field yet, so it's going to take us a while before we can actually solve for voltage. That being said, instead of trying to figure out all the steps that you're going to need by back engineering your sequence of equations, let's just start taking what we know from over here and filling in the gaps that we can fill in. So what we know already is that we've got mass of the oil drop, and we know acceleration due to gravity, or the force of gravity. And that is force equals mass times acceleration. So let's go ahead and just solve for that. Start filling in this blank. So force, I'm going to use blue pen. Force equals MA equals 2.54 10 to the negative 5th kilograms times 9.8 meters per second squared, which is going to equal 2.4892 newtons. Kilograms meters per second squared is newtons. But, 10 to the negative 4th newtons. But since we know from the last part that we're going to be solving, we want this in significant figures, we can go ahead and just do that now. Make it a little easier on ourselves. So that's going to be 2.5 10 to the negative 4th newtons, because we're using 9.8 as our acceleration due to gravity. So 2 significant figures there, 2 significant figures in our answer. If as you're going through this, you're using the answer key or previous answers on your calculator, you might get slightly different numbers. That's okay. It's going to equal out at the end. It'll be close enough. And you'll end up with the same answer. So we've got force of gravity over here that we can fill in now is 2.5 10 to the negative 4th newtons. We know, based on our diagram here, that the force of gravity is equal to the electric force, or force due to the electric field, rather. So that's also going to be 2.5 times 10 to the negative 4th newtons. Sweet. Filled in a few more dots over there. So now what do we have left? We've got voltage and strength of electric field remaining. Can I solve for voltage yet? We've got the distance. Still don't have the strength of the electric field. But I know force, and I know the charge. So we're going to have to rearrange this equation and get strength of electric field E equals force over charge, F over Q, which is going to be 2.5 10 to the negative 4th newtons over charge, 3.6 10 to the negative 9th coulombs, which is going to give us 69444.44, but we don't really need that many places out here, right? So we can just simplify that with our significant figures as 6,900 or 6.9 10 to the 4th newtons per coulomb. So we've got our electric field strength now. And let's go ahead and plug this in over here. 6.9 10 to the fourth newtons per coulomb. So now, volts is the only thing we've got left over here to solve for. Using this equation, we know E, we know D, so we can solve for volts. So V equals E, D equals 6.9 10 to the fourth newtons per coulomb times our distance, 4.8 10 to the negative fourth meters. It's going to give us 33.12 volts. But because we want this in significant figures, just going to be 33 volts. Two significant figures, same as all of the units that we've been using. 4.8, two significant figures. 3.6, two significant figures. This one up here has 3, but because these other ones have 2, we're just going to stick with two significant figures. And this is our final answer. You may have gotten 3.18 volts. And that's okay if you did your rounding a little bit differently. You may have gotten a number up here, 69.144, if you used your answer, and that's also okay, because down here, because of our significant figures, it's still just going to be 33. So there is your answer to 2012 question on static electricity.